I'm Jignesh Patel. I'm a new professor here at Carnegie Mellon. I've been working in the area of data for a while now, and the focus of my research has been on scalable and usable data platforms. And today I'll describe to you some of the research that's ongoing in my group here at Carnegie Mellon. So first, as a general background to why this is interesting, data platforms are everywhere. They power all critical enterprise settings today, and databases, which is the area of my research, are the workhorse that make it all happen. In fact, you've probably interacted with the database in the last hour. If you were on a social app, or you were on an e-commerce site like Amazon, or interacted with a financial service, all of those use database systems to provide that robust data services in a way that is not only efficient and fast so that your interaction is seamless, but also to make sure that any changes that happen to that data, if you withdraw money from your bank account, for example, that what is in your bank account after that transaction is accurate and correct, in spite of things like hardware failures and stuff like that. So data is everywhere, and all people everyone interacts with data. So my research is really broken into two themes. One is on system efficiency, and I'll describe a couple of issues in that area next. And the key goal over there is to figure out how to scale systems as data volumes grow. We as human beings are constantly collecting more and more data and digitizing that. The amount of data that we collect doubles every few years in many enterprises. And how do we store that, query that, analyze that in ways that are efficient? And the key targets are to make that both cost and energy efficient, right? You don't want to spend more and more as your data volume increases. You ideally would want your cost to go down or at least stay constant as you manage larger databases. The second aspect, which I won't spend a lot of time in today's talk, but I'll show you a brief video, is on human efficiency. How do we as humans interact with all these data systems that are pervasive and all around us? And how do we lower the barriers so that anyone can ask meaningful questions on this data, not just programmers? And so those two themes are obviously synergistic, right? For human efficiency, you need efficient systems. And for systems to be efficient, the reason we collect all the data is so that humans can get value from that data. So these two work together. Emphasis across both these themes for us is to work on problems that are meaningful and have practical impact. And in fact, some of the work that we've done over the recent years has made it into systems like Twitter. Some of our work powered all of real-time services at Twitter. It's called X now. And if you hate Twitter, I apologize for it, but it's a service that powered, our technology powered the underlying Twitter platform worldwide for many years. Last year, some of the work on efficient data processing made it into SQLite, which is the most deployed database system on the planet. In fact, in your phone, there are probably multiple SQLite databases, and some of the code for how to make SQLite run faster is probably running on your phone right now. So what is the big research problem? Obviously, data systems are everywhere. They are delivering value in applications all across. But what does the future look like? So this is the key area of focus for my research on scalable data systems. And as I've alluded to, data volumes continue to grow. On the left here is a chart that shows how much storage devices are getting created by vendors across, storage vendors like disk vendors, memory vendors. And as you can see, that is going up at a pretty alarming rate. And the vendors are creating this additional storage not because they just want to create it, they're creating because there's a demand for it. This is basically a quantitative way of describing that data volumes are increasing at a really fast rate. At the same time, a little bit more technical, but in the past, since 1980s, computers were getting faster every 2 or 3 years. It's something called Moore's Law. And one of the things that you could do is that if my data is doubling in size and the underlying computer and storage is doubling in its capacity and speed every few years, the way I would deal with more data volume is to just buy the next computer and run my database software on it. And essentially, this larger amount of data I can run at the same speed on this new hardware. But that has stopped because of various physical limits we are hitting with computing. So how do we handle this problem? If we don't handle this problem, obviously, as data volumes continue to grow, our cost of managing the data will rise, and at some point, it'll become unaffordable. So we need a way that is more cost-effective. So one way to do this, and the focus of our research investigation, is to do more with less. And the basic idea is, if you look at what happens inside any computing device, let's say even a very simple calculator, right? There's a processor inside, and you add two numbers. It comes back to you. Underlying, it takes a certain amount of time, and those are measured in cycles. Most computers run at many billions of cycles per second. And this operation of adding two numbers happens in one cycle. So 1/1000th of a second if there's 1 billion cycles being executed on that processor. But actually what's happening at the circuit level is that that number is represented in some form, and it probably is represented as a 32-bit or a 64-bit number. And so each of these bits, and I'll explain a little bit more in the next slide, is being operated on, and that one cycle, all of those operations were getting carried out simultaneously. So there's a lot of parallelism inside the circuits that power all of this computation for us. And can we get closer to that hardware, to that circuit level, and get more performance for our data systems? So here's an intuitive idea, and I'm going to keep this high level. Imagine I give you a list of numbers, 10 numbers that you see on the screen here. And I say, find from this list of 10 numbers, all the numbers that are less than 2000. What are you going to do? You're going to scan that list of numbers from left to right. And as you do that, you're going to pick the number that matches this search criteria and select that. Now, of course, as you do that, you've scanned this list from left to right, and it takes some cost. And that's the cost we are interested in. So what we'll do next is write these lists of numbers in a grid. And then we'll count how many grid cells we have to read from to answer this question, right? So this is really simple. That's my list of numbers. I put it in a grid. As you can see, the first number is here. And to run that algorithm that I just described, scan from left to right, which is pretty much what computers do today. When you give them a list of numbers and ask them to search, they'll go left to right. And I have to effectively scan 40 cells to pick the two numbers, the fourth and the sixth number, that are the result of my query. Now, what if you did something really different? And it's going to look weird to begin with, but I'm going to write these same set of numbers, same information, but in this form. This looks really different, right? This looks very different than what we just saw here. What's happening here is I've taken the first digit from each of these numbers and put them together. I wrote that in my grid cells at the front. So I've got the first digit for each of the 10 numbers together, 66, 815, and so on. And now I just search to that first 10 cells. That's my cost now. Instead of 40, just 10 cells. And I identify that the numbers that are interesting here are that fourth and the sixth number, right? I picked up those ones. I know that's my answer. Now, of course, I have to do a little bit more work, perhaps, to go get the rest of the digits, but I can just jump to that. But effectively, for the main part of my work, all I did was read 10 cells as opposed to 40. So there's obviously a huge amount of savings that you get from that. So this is an idea of how I can use algorithms working closely with how these queries are processed, in this case, just searching through a list of numbers, which is a very fundamental operation, and do that much faster. So just rethinking very basic principles of data representation and data accesses. Now, of course, computers work in binary form, right? What I showed you in the previous slide was in the decimal system, right? Just to keep that example accessible. But in the binary form, I'm going to have, for example, if I have a number 10, it's going to be 1010. But the same idea applies. I'm going to splatter the digits around in a very systematic way with a precise algorithm. And then as I go and work on answering these questions, I'm only going to look at the values bit by bit. So instead of, we generalize this a little bit, instead of looking at just the first digit, sometimes I may have to also look at the second digit and so on. But the advantage of doing this is that in many cases, I don't have to look at all the bits. So I get an advantage algorithmically of not having to examine as much data. I get the same correct answer, but with a lot less work. In fact, you can build a probabilistic model saying if I've got 32-bit valued numbers, which is a common representation for numbers in computers, what's the chance that with this new method that I mentioned, that you would not need to look at any additional bits. And you can create a probability model, and that comes up with an answer that says 80% of the time, after having looked at just the 8th bit, you don't need to go any further. And so that's the advantage. And of course, we've rendered this into practice. And this technique is called bit weaving. Here is the cost to go run scan operations like the one I showed you before. As the size of the code, the number of bits I need to represent the numbers increases. And the top is what most database systems do. It's a simple scan, the very basic algorithm we started with. This is what people do if they have specialized hardware that allows that scan to go faster. And we don't need any specialized hardware. We'll run on regular processors. As you can see, it's a lot faster. Okay, so this is a good example of doing more with less. There's a bunch of other stuff that we do in our group, very much related to that, working with data structures that run closer to the circuit level where everything's organized as bits and everything is scanned as bits, and operations on bits are often the workhorse primitives over which everything is built. Here's an example where you can take that bit weaving stuff and actually embed that inside storage, DRAM storage that you have on all computers. And effectively, as it is getting scanned, perform this type of operation for searching inside the circuit itself. And so what that gives you is by simply retrieving the data, you can also apply the scan. Effectively, you're getting the scan for free if you can make this work at the hardware level. Now, of course, this is all very research, working with a bunch of collaborators to push these ideas forward to see how close can this hardware and software synergy with this new class of algorithms work to get us even faster ways of doing data processing. Our research in this area is to build these new class of data processing systems called bit parallel databases. And they are at the intersection of course, algorithms like I described to you, architecture, and using techniques from compilers to be able to generate code on these novel architectures in ways that are efficient. So that's really a highlight of that research on high-performance data platforms. Tentatively, the project is called Hustle, and what we are shooting as a goal is with these new class of algorithms, working closely with the hardware and techniques for code generation using compiler methods and programming language techniques to be able to get within a next decade or so, 100x improvement, 10x from the algorithms, 10x from this close synergy with the hardware, to get 100x improvement in what data platforms can do from today. It's a lofty goal, but that's what we are shooting for. Okay, I started this talk by describing to you that there are two aspects of my research. I've spent all the time so far describing to you on novel ways that we are exploring for looking at building systems in a different way for data platforms so that we can scale these data platforms for the future requirements. I'm going to spend just a minute on the human efficiency part, not going to spend a ton of time. I'm going to play a video on the key project that we have, which is now a startup, where what we allow users to do, and remember the goal here is to allow users to access and ask questions on data with as low a barrier as possible. The lowest barrier is to put a ChatGPT-like interface for tabular data. And that's what data chat is. It's based on research from my lab that has been spun out into this company. And you simply upload a structured data file like a CSV file, a point to a database, a data warehouse, and just start asking questions in natural language. And it generates the code and produces the answer. And it'll also take care of figuring out if in creating the answer, it needs to run machine learning algorithms or regular data processing algorithms like SQL queries, or if it needs to do both of those and also produce rich visualization. So that's the lowest barrier to entry. Just point to your data, ask questions, get responses. The scope of this is on tabular data, right? So CSV files, as I mentioned, and structured data that comes from warehouses. Lots of research questions on how to do it efficiently, do it in a low-cost way, and do it in ways that uses computing surfaces like CPUs that are available everywhere, because the cost of overall deployment is also a major issue. So with that, I'm going to stop. And of course, if you're interested in this research and want to find out more, my website is jigneshpatel.org. Thank you so much for listening, and I hope I hear back from some of you.